Good morning, I'm Rosita and I'm now going to present a versatile, responsive hydrogel based on a high-performance dye, colorimetric pH response and food applications. Novel technology called active dyes designed to interact with parameters and analytes of the surrounding environment by modifying their colorimetric pattern, forming the concept of functional dye. Currently, the use of functional dyes in food science is rapidly expanding, involving applications such as smart food packaging systems, which consist of a small tag attached to the food packaging, monitoring the freshness or condition of packaged food. Many synthetic dyes are easy to obtain and have a production process with lower cost when compared to natural dyes. Generally, low molecular weight or small synthetic dyes are chosen based on their high absorption coefficients and/or emission QY in the desired medium. Other fundamental requirements leading to the design of synthetic FDs are the strong interaction with the analytes, the intense color fluorescence response, the fast response time, the selectivity, the reproducibility, and the reliability. The chance of modulating and optimizing these features even more justifies the use of small synthetic dyes. Hydrogels are three-dimensional networks consisting of polar functional groups swollen with a large amount of water. Due to their water content, porosity, and consistency, hydrogels enable a wide range of uses, from tissue engineering to food science. Their sensing ability and stimuli responsiveness to light, pH, temperature, and solvents is well established and increasingly exploited. Colorimetric gel sensors are a class of flexible, moldable devices able to change their color and absorbance spectrum under specific stimuli. They can work as miniaturized real-time analytical devices, providing a fast, simple, and low-cost response to parameters related to the freshness and spoilage of foods. Many sensitive and rapid pH indicators integrated in a soft aqueous matrix have been proposed for food applications. Simple visual tests rely on the naked eye transducer. Over the last 20 years, in addition to conventional spectrophotometry, a variety of complementary techniques have gained ground, thanks to modern automated analysis technology such as specialized reading devices and machine learning. Visual analysis has become increasingly smart and effective. The most recent approach to colorimetric sensors want them integrated with wireless technology, incorporating new electrical and optical features. The use of handheld devices such as smartphones is powerful and reliable and widely available to the public. Recent efforts in quantitative readouts of optical signals led to the development of smartphone-based approaches, creating targeted apps for a real-time analysis of the colorimetric signals captured with the smartphone camera. The smartphone camera replaces the human eye to obtain much more precise quantitative information. To quantify the digital color information to analysis algorithms with color processing and comparison were implemented based on the CIE 1931 chromaticity space. The CIE color model is a mapping system that uses three stimulus values, a combination of three color values that are close to red, green, blue, which are plotted on a 3D space. When these values are combined, the CIE space is supposed to be able to accurately represent every single color that the human eye can perceive. In our work, we developed a hydrogel-based pH sensing system named T-gel with a specific color display between pH 2 and 12. Use of agar as a non-toxic and low-cost polysaccharide was due to its unique ability to form strong gels in aqueous solutions. A responsive porous hydrogel easily molded into patches or tablets was obtained by co-gelling a single pH-sensitive dye and agar. The novel synthetic dye was designed to obtain large absorbance coefficients and colorimetric variations over a wide pH range, in addition to perfect miscibility with the matrix. The performance of the sensor was tested in different environments, both in solution and in the gaseous phase. The colorimetric pattern was monitored in water as a function of pH and in the vapor phase as a function of time. As practical application, we verified the sensor's ability to monitor food freshness through contact with untreated milk samples at different storage times. Our novel dye named T-dye was synthesized as summarized in the figure. The two hydrogen bonding hydroxyl substituents prevent isomerization of the hydroxyl bridge and stabilize the imine bond, even in strong acidic and alkaline environments. The alcohol chain increases the flexibility and solubility of the chromophore, and the OH groups improve solubility in water-containing solvents and the agar gel. The T-gel samples were prepared by mixing 6% grams over milliliters of agar powder with milli-Q water brought to a boil for 5 minutes, reaching approximately 100 Celsius degrees, while stirring until complete dissolution. After dissolution, T-dye was added dissolved in acetone at 2% by weight on the dry agar. Acetone was removed by heating the mixture for another 2 minutes at 100 Celsius degrees. The obtained solution was cooled in air, pouring it into cylindrical molds. Pyrex glass micro beaker was employed, obtaining 15 mm diameter per 12 mm high, transparent round samples. The gelation was allowed to proceed at room temperature. Swelling behaviors of hydrogels. Swelling ratio and water retention ratio are key parameters for the hydrogels as they measure the ability to maintain the water reserve necessary to act as a sensor. Both swelling ratio and water retention ratio are function of time and depend on two processes: the penetration of solvent molecules into the inner free space of hydrogels, relaxation and expansion of the polymer chains after absorbing the solvent. For T-gel immersed in water for 10 minutes, swelling ratio reaches 105 grams over grams. 1 hour later, swelling ratio rises to 1026 grams over grams. After 6 hours, the equilibrium swelling is reached with the swelling ratio around 3900 grams over grams. The T-gel sample, after reaching the equilibrium swelling at pH 7 and 25 Celsius degrees, was reused in water retention ratio test. Specifically, the water retention ratio parameter of the sample with initial swelling ratio 3 1,900 grams over grams in air at 25 Celsius degrees with the humidity of around 40%, was found to remain around 80% after one day and still 65% after 3 days in the same conditions. According to such results, we claim excellent water retention capability of our hydrogel samples, which implies the possibility of using stable tea gel samples even for long-term pH monitoring. The morphology of tea gel was investigated by SEM analysis. In figure are shown the SEM micrographs of the hydrogel surfaces at different magnifications. The surface of the hydrogel is quite rough, but uneven microphore distribution, rather rounded and of variable dimensions. The porous structure offers an advance for the use of tea gel as a permeable microspongy medium where protonation, deprotonation equilibria easily and rapidly occur. Colorimetric response of tea gel is buffered aqueous solution. A series of tea gel roundlets were obtained, balancing the speed and homogeneity of the response with the long life of the sensor. Due to the excellent performance of tea dye, a low dye content 2% weight of the dye relative to dry agar was sufficient for a clear response in all experiments. The color display of tea gel at various pH values were investigated by employing the CIE 1931 red-green-blue color space. For CIE coordinates determination, tea gel samples were immersed for 1 minute in water with a Britton-Robinson buffer at pH from 2 to 12. The different color shape can be naked eye detected for intervals of 1 pH unit. The related CIE coordinates are reported in the table. The colorimetric pattern was monitored by the mobile app named Red-Green-Blue Color Detector on the smartphone camera Samsung S9. Interestingly, samples from pH 2 to pH 7 displayed the gradual enhancing in the yellow color. Points marked in red falling in the green over red region of CIE diagram, while from pH 8 to pH 12, a blue complement adds, obtaining the gradual enhancing of the magenta color. Points marked in blue falling in the red over blue region of the CIE diagram. This behavior is associated with the hydrogen transference in the two phenolic functional groups. The calibration curve was obtained by plotting the varied intensity ratio of red over blue versus the pH. The plot shows two linear trends at acidic pH and basic pH with a good fitting linear coefficient. Colorimetric response of tea gel to acid and alkaline vapors. The colorimetric detection capability in the presence of acid and alkaline vapors was tested on a series of tea gel samples. Several hydrogel tablets were kept in contact with ammonia vapor of a saturated solution in a sealed vial. Different exposure times were evaluated and the colorimetric response was recorded at 5, 10, 15, 20, 25, and 30. The samples were photographed immediately after exposure through after 24 hours they show unaltered color. The sensor, originally yellow-orange in color, pH 7, records the presence of ammonia even for a minimum exposure time with a gradual intensification of the purple color. On the other hand, another series of T-gel tablets were kept in contact with hydrochloric vapor of a saturated solution in a sealed vial. Different exposure times were evaluated and the colorimetric response was recorded at 5, 10, 15, 20, 25, and 30. The sample were photographed immediately after exposure through after 24 hours. They show an altered color. The sensor, originally yellow-orange in color pH 7, records presence of hydrochloric acid even for a minimum exposure time with a gradual intensification of the yellow color. The exposure to acid alkaline vapors causes a strong color modification, more evident in the case of alkaline vapors. The examples exposed to acid vapor display the gradual enhancing in the yellow color. The points marked in the red fall in the green over red region of the CIE diagram. Samples exposed to the alkaline vapor display the gradual enhancing in the magenta over violet color. The points marked in blue fall in the red over blue region of CIE diagram. The calibration curve for the response in the gaseous phase was obtained by plotting the varied intensity ratio of red over blue versus the exposure time. Also in this case, the plot shows two linear trends at acid pH and alkaline pH, both with a good fitting linear coefficient. The intensity of the colorimetric response increases compared to what occurs in the buffered aqueous solutions, plausibly due to the greater vapor permeability of the porous structure of T-gel. The colorimetric response is immediate and even reversible. Samples subjected alternately up to 5 times to acid and basic vapors return similar color and CIE coordinates. In this slide, you can see application of the T-gel indicator for monitoring milk freshness. T-gel samples were used to monitor real milk samples and milk model samples. In this slide, you can see the application of the T-gel indicator for monitoring chicken spoilage. T-gel samples were used as an intelligent packaging placed in a PE capsule separated from the food sample consisting of 2 chicken thighs. A responsive soft matter sensor was obtained from a novel pH-sensitive dye in agar matrix. The dye shows high chemical stability, wide colorimetric variation in the pH range from 2 to 12, and high color intensity. The gel samples show excellent water retention capability. Swelling ratio is around 3,900 grams over grams when reached the equilibrium swelling, and good compressive strength, 20% compression under 120 kilopascal before the breaking. T-gel provides a colorimetric response according to different linear trends to acid and alkaline pH conditions. The colorimetric pattern was monitored in water as a function of pH and in the vapor phase as a function of time. T-gel tablets were used for colorimetric monitoring of freshness of milk samples and spoilage of chicken samples. T-gel could be a smart tool for the consumer to monitor food shelf life via a smartphone device. Thank you for your attention.